So you've got an actual brain.
Yes, these are your gloves.
Okay.
And that's my set. And we'll wear them because we have to wear them because these brains have paraformaldehyde in them. And so for safety reasons, we have to have our gloves on. So
What do they have again?
paraformaldehyde, that's what keeps the brain tissue fixed.
Okay.
Okay, so shall we take this
Yes.
particular brain out and take a look?
So if I touch it from my bare hands, what will happen?
Probably not a great idea because you might have a situation in which you might get some rash
Okay.
because there's paraformaldehyde in it. But I can give you some now in your hand. Now I can give you the brain. This is a goat brain. And it does in many ways resemble our brain. As you can clearly see, it has a lot of these folds, right? Because most of this tissue is folded now. So that's the gyri and sulci of the brain. That's what you imagine when you see a human brain. But this is a goat brain.
But is my brain like this?
Your brain is bigger than this. It's about 1.5 kilograms. This is clearly not 1.5 kilograms. This must be about 200.
But does it feel the same?
It feels the same if it is fixed. The human brain would feel the same if it was fixed.
Okay.
And so if you were looking at a fixed human brain, it would be larger. It would be about this much. And this is much smaller. But many of the structures are shared between the goat brain and our brain.
Tell me one major difference between our brain and goat brain and one similarity.
Okay. One big difference is if it was a human brain, the cortex, which is this part, would be much bigger. You wouldn't be able to see the cerebellum because the cortex would have expanded and flowed over the cerebellum, tucking the cerebellum underneath. So this would not be visible in a human brain as easily because this has become
This is
so
bigger.
large. In evolution, this has grown so big that it has flowed over it on either sides and this has got tucked in.
Okay.
Okay. The other big thing is, you remember we stand on 2 feet, right? So
Yeah.
we bipedal. So this, imagine if this was a goat, this is its head and it has 4 legs. This has also moved like this. So you would see the human brain, this would be tucked underneath. This would be much bigger and flowing on either side. The spinal cord going down like this rather than the spinal cord coming out.
Oh, so this is like...
This is the beginnings of the spinal cord. From here would come out the long spinal cord with nerves coming out on either sides that control the limbs, the rest of the body. That's one obvious difference. Obviously,
Interesting.
the size is a big obvious difference.
But where does, let's say, the part which, let's say, in humans, because we are more desirous, so where the desire and ambition and all of that plays out in the human brain versus an animal brain?
So goats have the ambition of also finding effective grass to eat.
Okay. Yeah.
They have that ambition.
Yeah.
We don't consider it the kind of ambition that we think of. But if a goat doesn't have the motivation to find grass, to find food, to drink enough water, it won't survive either. So the motivation circuits are actually fairly similar. The same things that make you want to go and eat are the same things that make you ambitious to want to land on the moon. It's the same underlying circuitry. It's just that it's doing very different things in humans from goats.
Okay.
But goats have motivation circuitry. Without motivation circuitry, the animal will not survive.
And physically, where is it? If you
It's in
can
the
point
structure
out.
called the ventral tegmental area, which will be right underneath this. So if you go underneath that, there's a structure there called the ventral tegmental area. And then there are nerves that go all the way underneath. Here is a region called the striatum. If I opened it up, you would see it. At the base of the striatum is a structure called the nucleus accumbens. That's where motivation resides.
Can I
it's-
just turn it around?
Yeah, turn it around.
So this is where...
So-
and in humans also it's similar.
It's very similar. It's very similar. That's there whether you are a rat, you're a mouse, you're a squirrel, you're a goat, you're a
Okay.
human. We all have that baseline circuitry in our brain. It's the same circuitry that makes you feel thirst and motivated to go drink water, eat food, have sex. These are all the same underlying building blocks.
Under the brain.
It's inside.
So
it's embedded underneath here.
And what is protecting? Like what's the outside?
This stuff right here, coming out of here would be your pituitary,
What does it matter?
which makes all the hormones of your body. The testosterone, the estrogen, the thyroid hormone, all of those hormones that go everywhere in the rest of the body and do the job of, hormonal control and metabolism, come out from a little stalk, which has now gotten chopped off. But here's the hypothalamus and the pituitary would emerge from here. You can also see it in
Interesting.
you would see the same thing if I gave you a rat brain, okay? So
This is a
now
rat brain.
That's a rat brain. Now what is obvious to you first and foremost is this is smooth. And this is curly and wrinkled, and that is absolutely smooth.
And why is like that?
That's because the cortex is relatively less in size, and in the skull it fits. without having to fold.
Okay.
Whereas in the goat brain, the cortex is already expanded, and for it to fit, it has to fold. So if you take out this cortex and flatten it, right? Like if you flatten it out, it would be a 1 rupee coin. If you take this out and flatten it out, it'll be like a small puri.
Okay.
If you take out a monkey brain and you do the same thing and flatten it out, it'll be a largish chapati. And if you take a human being brain and flatten it out, it'll be a pizza.
It'll be that big.
It's big. So now, but the skull hasn't commensurately expanded. We are not walking around with skulls that are this big, right? Like mega mind. We have small skulls. So now the stuff has to still fit. So to fit, it has to fold and fold and fold. And that's wrinkles. Why you have these folds, which are called gyra and sulci. And here you don't need to fold. Because so it's a smaller. Smooth brain. It's called a lysensphalic brain, which is a smooth brain.
But here's a question. So these brains are preserved brains.
Yes.
Right?
Yes.
What's the difference between a live brain, which is probably right now in my head or in some living animal, versus a dead brain and versus a preserved brain?
So a dead brain, suppose we just took the brain out of the body, then there would be a lot more blood that would be immediately visible. The brain receives a large amount of your blood supply. So you would see blood, which you don't see here at all because the blood has been removed and cleared out. Okay. Also, it's significantly softer because when the tissue dies, the cells start dying. And as they die, they literally dissolve away. There are all these enzymes that are chewing up stuff. It will fall apart. If I give you a live brain, in a few minutes, it'll start falling apart.
Okay.
Here, this is preserved because it's had formalin, or it is. A lot of people would have seen this in school when you go into the laboratories and you see things in these long jars, and you see one snake or you see some body part. It's been preserved. It's been preserved by using formalin or formaldehyde, which preserves the brain, and now this will stay like this for actually years.
Interesting. But does it change anything in while you're researching or doing anything?
It does change things which we can't easily test in this. So for example, if I want to look at RNA or DNA or look at the genes that are being switched on, I can't do it in a preserved brain. I have to do it in a live brain.
And does it shrink in size?
It does shrink a little bit because this sort of formalin, once you cross-link proteins, things become tighter. And because they become tighter, things become more tightly connected. It does shrink it a little bit. So it is a little bit smaller, but not a lot.
And now that this is preserved with all these things, what can this preserved brain tell you about a living brain which is inside my mind?
So you can cut this into sections. So let's put this fellow back right here. And let's take that and let me show you its younger or other evolutionary relative, that's the mouse. So you get a sense of how the mouse brain.
Wait, mouse and rats are different?
They're two different things. I know we all say chua and we think that the chua is just a chua.
Okay, is it a genuine thing or am I like really dumb?
You would not be the first person who's asked this question. So people are like, rat and mouse, isn't that just the same thing?
Yeah.
You've seen a big rat, right?
Yeah.
And you've also seen these little, but they're not baby rats. They're actually mice, which is a totally different species. So that is a mouse brain and that is a rat brain. And so the mouse is significantly smaller. It's like about 25 grams, an adult mouse. And a rat, adult rat would be about 250 grams. So
the big ones,
significantly bigger, right?
The one you see on train stations, and that's
the one you see on train stations is this. The one that's probably wandering around in your house in the corner, which is eating up the food, is more likely to be a house mouse. Yeah. But you can see that it's very similar. Even though these animals have very different sizes, they have very similar lifestyles. They're also, nocturnal. They like to they come out at night. There's a lot of biology that's very similar, even though they're different species. And you can study a lot by studying these animals because the rules are common many times across this, and what's here.
What are common rules?
The neurons that do all the processing in the brain, they're similar here, and in our nervous system. The way they're connected and the way they're networked is different, but a lot of the basic building blocks are very similar. It's like with a Lego box, you can make a simple thing, you can make a complicated thing, you can also make something that's very, very... So the building blocks tend to be very, very similar, but as the complexity goes up, you get different function which emerges from these networks.
But so you were telling me this, that when you study these brains, what do you find out about human brains?
Yeah. So let's take a look at the microscope and then you'll see what is actually inside the brain and you'll realize that the rules are really, really quite... So let's say I want to see how neurons function. Okay. We can move this microscope closer to us. Let's take our gloves off.
Or maybe we can just finish this. Is this done? Or you were going to cut?
I wanted to cut. So let me cut then maybe and show you that and then we can go to the microscope. Okay. So I'm going to section...
actually cut it.
Yeah. I'm going to take a brain here and put it into what is called a mold. Okay, so this is a mold. So I'm just slicing the brain now. I'm just going to put it in a mold like this. Fit
Okay,
it
so
in
this
here.
mold is for this mouse
This mold
brain.
is for a rat brain.
Okay,
I have a mold for a mouse brain, which is right here, which is a smaller mold.
Okay.
Right? But we'll use a rat brain mold, and I'm going to cut right here. Okay, that's one.
How difficult it is or easy is it for you to cut?
This is easy. When we want to cut really thin, you need machines.
Okay.
So we cut down to like fractions